Hello everyone, I'm Zixiao Zhang from Group 16. In this project, we focus on the hybrid PFM APWM controlled LLC resonant converter. Here's our team members. LLC resonant converters are widely used in sustainable energy systems such as photovoltaic inverters and energy storage systems because of their high efficiency and soft switching capability. However, conventional converters using pure pulse frequency modulation control face serious limitations. To maintain soft switching, the switching frequency can only vary within a limited range. When the input voltage exceeds this range, for example, during large PV voltage fluctuations, the converter either loses regulation or leaves the soft switching region, causing higher switching losses and lower efficiency, sometimes dropping by more than 10%. To solve this problem, our project proposes a hybrid control scheme combining PFM and APWM. Under normal input conditions, the converter works in PFM mode to maintain high efficiency. When the voltage goes beyond the soft switching range, it automatically switches to APWM mode, dynamically adjusting the duty cycle to expand the voltage range while still keeping soft switching. This hybrid control improves both efficiency, stability, and voltage adaptability, making the converter more suitable for renewable energy applications. In the following sections, my teammates will explain the detailed control principle, simulation design, and results.
Hello, this is Xiaokang Lu. I have completed the construction of Simulink simulation model, and next, my teammates will respectively introduce the overloop and closed loop simulation models.
Hello, I'm Chen Xie, and in my part, we will look at an LLC resonant converter under PFM control. The gate drive duty is about 50%. Counting the dead time, the effective duty for each device is roughly 44%. Regulation is done by moving the switching frequency around the tank resonant frequency. The VCO generates a sinusoidal carrier whose frequency changes with the input voltage. When the input is 1, the output frequency is about 100 kHz. That carrier is then compared with a 12-volt reference in a comparator. When the VCO output is higher than the reference, the comparator goes high, otherwise it goes low, giving us the PWM3 modulation signal. The continuous time whistle converts the control input into a switching frequency Fs. Two comparators check against plus and minus 12-volt references, plus 12 to 100 volts and minus 12 to minus 100 volts. A plus minus 12-volt dead zone avoid overlap. Then the LLC tank says FR. We classify operation by Fs. When Fs is less than FR means under resonance. The primary switch achieves ZVS at turn on and the rectifier current becomes discontinuous, so ZCS at turn off. When Fs is greater than Fr, the rectifier current is continuous. ZVS still achieves 0 voltage turn on, but you can see that at a turn off the current during ZCS is not 0, so ZCS falls. With PFM, soft switching means ZVS at primary turning on plus ZCS at a rectifier turn off only holds in the under resonant region, which narrows the usable input voltage range, so widen the range we bring in APWM.
Okay, now this is Qicheng Zhan. This section is a carrier signal generation and comparison unit of the APWM control circuit, mainly used to generate PWM3 signal and control the switching operation of the subsequent power transistors. So to make the circuit operate in a sub-resonant state, the input constant 1 fed into the continuous time VCO. The VCO generates a sinusoidal carrier signal whose frequency varies with the input voltage. This signal serves as the core driving waveform of the APWM control, determining both the switching frequency and duty cycle. As a result, the circuit achieves DCS soft switching, reduces resonant overshoot, and improves energy transfer efficiency and device's reliability. Now, this figure shows the voltage and current waveforms of the switch under APWM control when it achieves ZVS soft switching characteristics. As can be seen from the figure, at the moment of turn-on, the voltage drops rapidly to zero while the current remains close to zero and then gradually rises, indicating that the switch turns on when the voltage has already fallen to zero, thus realizing zero voltage turn-on. This process effectively prevents the overlap of voltage and current, thereby significantly reducing switching losses. Now, this figure shows the voltage and current waveforms of the switch under APWM control when achieving ZCF soft switching characteristics. The waveform demonstrates that through sub-resonant control, the current naturally crosses zero before turned off, achieving ZCF soft switching, which reduces switching losses, suppresses electromagnetic interference, and improves the overall efficiency and stability of the system.
Hi, this is Kai Guo, and my teammates have already introduced how our converters use PFM and APWM to achieve ZVS for the primary switches and DCS for the secondary rectifier diodes. Now, let me move on to the control loop and show how these functions are actually implemented and combined. The control loop monitors the output voltage and combines it with a reference, which is exactly the output voltage we want. We set it 12 here. The error is processed by the two PI controllers to generate the control signal, and we use this to add die time to guarantee soft switching. We have a comparator here. This value is exactly when it is the quasi-resonant. So when it's under resonant, it goes this way, and we use PFM to control frequencies. And when it's over resonant, we go this way, and we use APWM to control duty cycle. So through its closed-loop control, the converter can automatically switch between two modulation methods and maintain stable output and get soft switching. So let's simulate and verify this model. Under an input voltage of 380, as the simulation result, we achieve DVS and DCS. And most importantly, the output exactly 12, that is what we want. Then we can go back and just set the input voltage to 570. This should be over resonant, and this should be APWM control. And we see through the current and the voltage in the switching and the diodes. This is the simulation result. You can see that still DVS, this two here, we still have DCS. And you can see the output voltage is still 12, that's what we want. So this converter can get full range DVS and DCS operation. It achieves high efficiency and fast dynamic response and a very stable output voltage. But this design still has potential for further improvement. For example, the rectifier diode here can be replaced by the MOSFET switches because the voltage drop of a MOSFET is much smaller, and this can help us reduce the conduction loss. But that means that we actually need another drive circuit to control. So actually, our designed LLC resonant converter can be applied to high efficiency DC to DC power system and different scenarios, such as electric vehicle onboard chargers, which for now the electric cars are very popular here. And this converter is especially suitable for situations that require large input voltage range and low noise, and the situation that we want to get high efficiency. That's our project. Thanks.
Our proposed hybrid PFM APWM control has strong commercial potential. It can be applied to PV inverters, EV chargers, and energy storage converters, where wide voltage variation is common. Compared with traditional PFM control, our method improves efficiency, stability, and adaptability, reducing energy loss and cost. Therefore, it offers a more market-ready, high-efficiency power conversion solution for renewable energy industries. Thank you.